My talk for today is a language for building cognitive systems. And this is from my colleague Sheldon Linker, as well as myself. I'm going to talk about, I'm going to give us a brief introduction and then talk about the language, which is the premise language. And then we're going to give some examples in imperative programming, functional programming, declarative programming. We're going to take a look at the taxonomy, so all the different data types available in the language, and then show a multitasking example, messaging example, and persistence example. And then compare the language to OPS5, CLIPS, and SQL. So the premise language itself, it's a knowledge construction language which combines high-level primitives with object persistence. The language uses functions and prototypes. The goal of the language is to provide a platform for artificial intelligence programming. Software agents written in the language share a knowledge base where they can create, modify, and delete objects amongst themselves in a stigmergic manner. Premise is influenced by Lisp, Self, JavaScript, OPS, particularly OPS5, CLIPS, and SQL. And it facilitates declarative, functional, and imperative programming. Premise was developed by myself and Sheldon Linker starting in 2013. We got a first implementation going in 2014. And we've been working on various versions of it since then. And it's the language which we use to implement our cognitive architecture, the PSG modeler. So this is an example screen of premise. The interpreter. Imperative programming example in premise. Premise has about 430 primitive functions. The language mirrors Lisp, and it's actually a little bit different from Lisp in that Lisp is a what they call a symbolic language. When you type an expression, particularly an atomic expression, it evaluates as a symbol. In premise, we inverted that, and when you type in an expression, an alphanumeric expression, it returns as a literal. And so to differentiate literals from symbols, we prefix symbols with a question mark. We have a function called given, which functions as a let in Lisp, for anyone familiar with Lisp. So this particular example, says given a total as 0, step I from 1 to 10, and set total to total plus I. So, and then return total. And the answer is 55. So this is just a simple imperative version of this computing the numbers from 1 to 10. Summing the numbers from 1 to 10. A functional programming example would use recursion and take a list. And here we define a function called sum1. We take a list of numbers and we detect if the list is empty, return 0. Otherwise, we add the first number. So @ is used to take the first item, similar to car in Lisp, but at numbers, plus the sum of the rest of the numbers. So we get our function sum1 after the ergo sign. And then we have a function, built-in function called range, which gives us a range from a starting number to an ending number. And we can pass sum1 this list. It returns a list. In premise, we have something called a call and something called a list. So in the Lisp language, there's no distinction between lists and function calls. But in premise, function calls are wrapped with parentheses, whereas lists are wrapped with curly braces. So we can distinguish one from the other. So here we sum the range from 1 to 10 and we get 55. So declarative programming, in declarative programming, we declare relationships and we create instances of those relationships. And then we can match over those relationships with patterns and do particular tasks. So here we declare a relation called addend, and we have two slots, value and counted. Value has no default value, so it will default to nil, and counted defaults to false. And that gives us our addend. Then we can step I from 1 to 10 and create a new addend where the value is I, the value of the index. And so it creates individual addends, and in premise, when you create a new instance of a relationship, you get the relationship plus the instance number. Then we create a relation total where the slot is the only slot is result, and then we can create a new total. And then finally, we run a pattern over the knowledge base, over the relation. So we say with total, the caret is the instance ID slot. So with total as question mark total, and addend as addend, and value as value, and counted equals false. So we want to match all the uncounted addends. We put counted to true. So for that particular addend that we matched, we set the value of counted as true. So we indicated that the addend was used. And then we apply plus to the value of the result and the value and the current value. We put that in the result slot, and then we return the result for that instance, and that gives us 55. So the language is similar to Lisp in that symbols do not have a type. Symbols hold a data, and the data is typed. So we have a taxonomy of data types, and we have everything is a variant, and from variants we have something is either a thing or nothing, and nil is derives from nothing. We have atoms and we have containers. On the atom side, we have numbers, and we have complex, imaginary, integer, long, rational, real, floats, unsigned. We have infinity, negative infinity, and undefined as numbers. We have time, we have instants of time, and we have intervals of time. An instant, we have dates, epochs, which are Unix epochs. We have moments, which are nano years, which is about 3 milliseconds, I believe. We have seconds. We have ticks, which is 1 nanosecond. We have eternity and negative eternity also as time values. We have different kinds of literals from functions, different kinds of functions, different kinds of keywords. You have URLs, and we have on the container side, we have sequences, assortments. So assortments are basically unordered items. So, collections, configurations, enumerations, environments. We have relations and structures, which are record types, which are, record types, and ephemerons and thoughts. Thought is a persisted record, and ephemeron is an unpersisted record. And we have schemas, which correspond to a dictionary. Also, we have sequences. And so, as I mentioned before, we have calls, we have expressions. An expression is a list that is undelimited. So there are no parentheses around them at all. We have lists, which are denoted by curly braces. We have stacks. We have strings, which are denoted by double quotes. We have tuples, which are denoted by square brackets. And we also have vectors, byte vectors, which are denoted by pipes. So that's the taxonomy. And the primary motivation for the language, for creating language in the first place, was to do three things. We wanted to do multitasking, messaging, and persistence in a very simple way, because the systems we're building, interact with the database, but they also needed to do multiple things at the same time, so for parallelism, and they need to send messages either across the internet or just message each other. And so we wanted a language that would facilitate that. So in premise, the async, co, and task functions run expressions asynchronously, concurrently, or as required. The concurrence function co returns after all tasks have completed, whereas the asynchronicity function async returns immediately after invocation. The task function creates a task for deferred execution, and the functions each return a list of task handles. So in this example, we say async, step I from 1 to 3000, do something. That runs asynchronously. Step J from 1 to 6000, do something else. It returns two task handles, task 1 and task 2. We can query whether or not the task is finished by asking if it's ready. And we can await a task. And when we wait for the task, we'll wait until the task is complete. It'll return something. We can await a task with a timeout. So for example, we can say await task 2 for 1000 ticks, and return timed out if it doesn't respond. And so it returns timed out. Some more examples. We can cancel tasks. So we can step I from 1 to 100,000. If canceled, self, then break and return oops. Otherwise, return finished. We can step I from 1 to 1000, return finished. This gives us two task handles. We can cancel task 57. Cancel just returns the task ID. We can await task 57. It returns oops, because it detected that it was already canceled. And this is a cooperative task cancellation. We can abort a task as well, but that just will leave the task in a state that's not, it's an unknown state. And then finally, we can free task handles. If we run co, co will run all of the expressions that are passed to it, and will return the values only after all the expressions are done. And then we can also wait for tasks to be done, but here this is a little bit superfluous, because co returns the tasks. So yeah, basically we free task handles after we're finished with them. And then finally, just another example for task. So whereas async and co created and ran the tasks, if you just say task by itself, it will take each of the expressions and create a task handle, but it will not evaluate the task. Then it's up to you to run the task asynchronously or run several tasks concurrently and await their results. So for example, here we say async task 1 returns task 1, we can await the value and get the value. If we say async task 2 and task 3, we can await those values and get those values. Then finally, we can return all the tasks. So the other thing we wanted to do was messaging. And in messaging, we wanted to just keep it as simple as possible. So we have 3 basic functions to perform messaging. Tell, ask, and listen functions handle messaging. Tell sends a message to a URL. If the literal user is specified instead of a URL, then the message is sent to the console. Ask sends a message and returns a response string. If user is specified instead of a URL, then the input from the console is requested and returned. And listen creates a listener on a particular port. So for example, if you ask the user, what is your name? Then it'll await your input. And you input, and then it'll return whatever you input. You can ask, for example, http://msn.com and give it just a message, and it'll return the value from that URL. Truncated it here for space. You can tell the user, for example, hello world, and it will output hello world to the console. And it will actually also return the value told. Tell always returns told if it's successful. Otherwise, it returns a failure. And then for listen, you create a handler for the listen function. And so our handler in this case is reply. We give it a URL. It takes a URL and a message, and then the handler function will actually turn around and tell the URL that the message was received. So the reply is to respond back to the URL and say that it received the message. And then we say listen, and then this URL actually constructs a URL function. And we say listen, we give it the URL and the handler function, and it creates a listener. And the listener is listening on that particular URL, on that particular port. Then we can ask the port, and we can tell it secret. And then it will respond, received secret. And then we can free the listener. Persistence. Oh. Okay, persistence. So we have a few functions that handle persistence. The structure, relation, and new functions provide access to record types. The structure function creates an ephemeral record prototype, while the relation function creates a persisted record prototype. In the premise language, persisted records are called thoughts. Applying the new function to a structure will produce an unpersisted ephemeron, while applying new to a relation will create a thought. So in this example, we say structure fault, and we give it 3 slots, what, when, and where, and it returns the structure name. We can say new fault, what is an error, when is the current moment, where over here, and then it will return back a, we call this a premise, but it's a tuple with the type of the tuple type and then the slot values. And this is a moment. It's a nano year, and it's suffixed with an M. We can create a structure error that uses fault. So we can compose structures from other structures, and we can add an additional slot who, and we can say new error, who, my function, what, punted, when, moment, where, here, and it returns error, who, my function. It returns the tuple, basically. But this is unpersisted. So when you use new on a structure, it will not persist the values. Likewise, we can create a relation, and we can give it slots salary, name, supervisor, reclaim, and salary of method, salary year to date. And that will give us back the relation. And then we can say new employee, name, Jane Doe, salary, $2 million. And it will give us back employee one. And this employee is persisted, and the ID for this employee is employee one. If you ask for the premise of employee one, it'll return the complete structure. And so finally, we're just going to wrap up by comparing premise to OPS5. And so in OPS5, you would create a relationship by saying literalize, and you'd give it the slots. Here in premise, you say relation, you give it the slots as well. And then you have a production in OPS5, whereas in premise, you can have a rule. And finally, you can create a new instance. In Clips, which is a re-implementation of a production system, specifically of the art language from Inference Corporation, common C language implementation of a production system. You have def templates. Here we still have relations. You have def rule, def facts, and here you have rule. And instead of defining facts, we just have a function that creates the new facts. And then SQL, everybody is familiar with good old SQL. You can create tables, different kinds of tables. In premise, you just create relations and provide the slots. The slot, we can omit the ID slots because they're automatically generated. And inserts are equivalent to news. Updates are equivalent to looking for the particular pattern and putting a new value into the slot. And then deletes are equivalent to making the opposite of new in premise is old. So if you old a ID, then that gets rid of it. And that's about it. That's what we have for today.